use a substitution to integrate the double integral over this region R, 2x squared minus xy minus y squared dx dy. R is the region in the first quadrant bounded by these four lines: y equals minus 2x plus 4, y equals minus 2x plus 7, y equals x minus 2, and y equals x plus 1. A lot of these substitution problems you meet in the textbook are going to come with a substitution suggested or provided. I actually wanted to look through this one and see if we could figure out a substitution to try on our own. So the first thing I'm going to do is graph the region we're talking about here. And so I just have a bunch of lines to graph, and I know the region I'm talking about is in the first quadrant. All right, so I have the line y equals minus 2x plus 4. So let's see, the y-intercept is 4, 1, 2, 3, 4, and then down 2 and over 1. And let's see, that's going to hit the x-axis at y equals 2. So there's my first line. All right, and then that's 4, 5, 6, 7, and then that's going to hit at 3.5. 1, 2, 3. So we'll just use those 2 points. Now, if I do this right, these should be parallel lines. I've missed my point there, but good enough. All right, y equals x minus 2. It's going to go through that point right there. That's kind of nice. And then y equals x plus 1. So I see the region of integration. R here is this turned square, kind of a diamond shape. Not drawn perfectly to scale. Okay. And we can see that this region of integration would provide us some challenges if we just wanted to use rectangular coordinates. Because no matter the variable of integration, I'm going to have to look at multiple integrals to try to be able to integrate over that region. All right, so I've graphed it. Let's take a look at the integrand. And I don't know about y'all, but I'm thinking about factoring that. And so let's see, I'd have a 2x and an x. And let's see, minus y and plus y. Let's see, 2x squared minus y squared. And here I have a minus 2xy and an xy, which would give me that minus xy in the middle, and I feel good about that. All right, so I think this would be a healthy place for y'all to pause the video and see if you could guess what's going to happen next, what substitution I'm going to suggest. Okay, so let's see. I'm going to use the substitution u equals 2x plus y and v equals x minus y. Well, number one, because u times v is going to be easy, I hope, to integrate. And number two, when I look here, right, if I add 2x to both sides, to both of these, right, y plus 2x equals 4 and y plus 2x equals 7, well, that's u equals 4 and u equals 7, right? These bounds reduce, instead of being between these two lines, being between these two constants, right? I'm going to think about a u-v plane in a minute, so those two constants. And then here, let's see, well, if I rearrange this to be an x minus y, this equation would be x minus y equals 2, right? Take y away from both sides, I add 2, and this one is going to be x minus y equals minus 1. So I have v equals 2 and v equals minus 1. So again, this substitution makes the integrand easier, and it makes the region I'm integrating over much easier. So, the region G, let's see, u-axis, v-axis, v equals 2, v equals minus 1, 1, 2, 3, 4, 5, 6 is this region, right? I'm integrating over that nice and beautiful rectangle, and that seems like a much easier thing to do. And so this thing I started with is equal to the integral from 4 to 7 and from -1 to 2 of u times v times some as yet to be determined scaling factor, which might be a variable expression or a constant expression from the Jacobian du dv. So now what I need to do is use my substitution to calculate the Jacobian. So I need a function x equals g of u comma v, and I need a function y equals h of u comma v, right? These equations right now are kind of the way I would have done substitution before, where I'm like u equals something and v equals something. I need to solve for x and y so that I can calculate my Jacobian. So I'm going to put this stuff aside for a moment. And I have u equals 2x plus y, and I have v equals x minus y, and we need to solve for a system that says x equals and a system that says y equals. So I'm going to start with this equation, and I'm going to get y by itself. Y is equal to u minus 2x. Just take 2x away from both. What I can do is take this expression for y and plug it into this function. So v equals x minus u minus 2x. So now I have an equation that only has x's, u's, and v's in it, so I can get x by itself. So let's see, that's going to be 3x minus u. So x is equal to 1/3 u plus v. That's the substitution I'm actually going to be thinking about for y when I go to compute the Jacobian. Well, I still need an expression for y, and if I look here, y is equal to x minus v, and after I have that, I can simply substitute in the expression I already have for x. And there's more than one way to go about every single one of these problems. So if you thought about something else, I encourage you to go on and try that. All right, so x is 1/3 u plus 1/3 v, where y is 1/3 u minus 2/3 v. Now we can compute our Jacobian. In this first entry, I would have the partial of x with respect to u, which is 1/3. In the next spot, I have the partial of x with respect to v, which is also 1/3. And now I take the partials of y with respect to u and then v, so I end up with 1/3 and minus 2/3. Right, I'm running out of room here, but let's see, I have a minus 2/9 minus 1/9, which is minus 3/9 or minus 1/3. So now that I know the value of my Jacobian, I can come back here. Instead of minus 1/3, I'm going to put in 1/3 because that's always an absolute value. And now we're ready to integrate. I've made my substitution, I know everything I'm supposed to, and we have a very easy double integral to evaluate, and I think I'll just let my audience evaluate this very simple double integral, and that's it for now.